Hello, sir. Good morning.
Hi, Ravi. Can you hear me?
Yeah, sir. You're very clearly audible. Very good
Okay,
to see you,
great.
sir. Yeah, I hope
Yeah.
it is good afternoon at Malaysia this time.
Yes. It's afternoon. It's
Very, yeah,
2 hours
very good
ahead.
afternoon. Very good afternoon, sir. Sir, we are just
Okay.
waiting a few 4 minutes so that our more participant can join.
Sure. No worries.
Yeah, then I will request you to deliver. Please
No
submit.
problem. So
Yes.
how's everything there in India?
Yeah. It's so good, sir. Winter is going on and it's a chilling season this time.
I see.
Yeah.
Okay.
So it's very good to see you, sir, after so long.
Yes. I'm
Yeah.
now the Deputy Vice Chancellor.
Yeah,
Uh,
I,
University Malaya. That's right.
Yeah, you haven't yeah, you have told me in that previous discussion, I think. It's very great to see you, sir. I know that it is very difficult for you to just take this time out of your very busy schedule,
No
but
problem.
still,
Anytime.
sir, but still you have managed and accepted our request. So we are very highly thankful and delighted for the same.
Yeah, it's a Saturday here, so if it's a weekend normally it's not a big issue for me. Weekdays,
Yeah,
sometimes
yeah,
it's a problem because there's a lot of meetings and activities. So at the university, it's quite hectic. I normally at work till 7 p.m., 8 p.m. in the night.
yeah, yeah. I can understand, sir. So okay, sir. Just we are waiting for 1 or 2 minutes, then we will start.
Sure. No worries. Anytime.
Yeah. Yeah, so okay, sir. I think sufficient participant has joined us now. So just, I think we can begin with the session.
Okay.
Yeah. So, sir, before requesting you to begin with your talk, so I wish to just share some brief about yourself with our participants. So, dear participants, Professor Ramesh Singh sir is a senior professor in the Department of Mechanical and Materials Engineering at University of Malaya, Malaysia. He is currently serving as the Deputy Vice Chancellor, Academic and International at University Tenaga Nasional, Malaysia. He received his doctorate PhD in Advanced Materials in 1997 and Bachelor of Mechanical Engineering Honours First Class in 1994 from the University of Sunderland, UK. He has received many accolades as a distinguished professor and have an outstanding track record in administration, teaching, and research. He has served for 2 terms as an associate director for the Engineering Accreditation Department Board of Engineers in Malaysia and is serving in numerous capacities as a consultant and external examiner, expert advisor, reviewer, editorial board members, and visiting professor. Professor Ramesh has secured more than $5 million USD for research grants and consultancy projects so far. He has made over 350 scientific publications, including nearly about 240 peer-reviewed research papers, and has completed the supervision of more than 80 postgraduate students. He has received more than 90 awards and recognition for his work, including the prestigious Young Engineer Award from Institution of Engineers, Malaysia, the Malaysia Torres Science Foundation MTSF Science and Technology Award in the recognition of his outstanding research achievement. He is chartered engineer, chartered professional engineer Australia, and a professional engineer Malaysia. He is also serving as a distinguished professor in several universities in China also. Professor Ramesh research interests include the development of specialty ceramics and composite materials for versatile biomedical and mechanical applications, laser welding of metal alloys, failure analysis, material characterization, corrosion and degradation of engineering materials, engineering education, and there is a lot to say about Professor Ramesh Singh sir, but as the time constraints, I'm stopping myself here and welcome you sir, and session is yours. Please.
Okay. Thank you, Dr. Ravi. Good morning, everybody.
Yeah.
At NIT, thank you for inviting me for this faculty development program. I'm honored to be here, and thank you to Dr. Ravi for inviting me. Let me just share the slides, and then after that, we can take it from there. So, so just bear a minute with me. Yeah.
Yeah.
Okay. Can you see the slide?
Yeah, it is very clearly visible, sir, and you're audible
Okay.
also. Yeah.
All right. So thank you once again.
So
So
make
it's
it
an
on full
yeah,
screen, I think. Make it on full screen so it will be more clearly visible. Yeah.
yeah. It's on full screen now. Can you guys see it?
Uh, okay, but not full screen is coming to us. Actually, entire screen of yours is coming. Yeah, it is on full screen. Sir, can you please keep on changing slides so that we can confirm the changing of slide?
Okay. I've changed the second slide.
Okay, so it is not coming like, so please can you just cancel it and just reshare again? I think it will work like.
Okay. Just 1 second. Okay. What about this?
Yeah, it is coming.
Okay. So I think maybe the delay is with when I
Yeah,
present as a PowerPoint. So then so this is okay. Yeah. Is this
yeah.
okay?
So now just make it on full screen. I think it is now on a just a small screen is coming. So just Yeah,
Okay,
clear.
now it's full screen. Can you see that? Now I've changed to the second slide.
Mm, I
Not
think,
coming through. Third slide.
yeah, not. Sir, can you please reshare? I think just select the entire screen, then share. I think small screens are
Okay,
just coming.
just 1 second.
Yeah.
I reshare. Okay, I've cancelled it. Okay, let me try to uh, let me try to do it again.
Yeah. Select the entire screen and share your screen, then PPT will work maybe.
Yeah, just 1 second.
Yes, sir.
Okay, can you see the screen now?
Yeah, yes, yeah. Screen is
Okay, I'm going to
visible.
the second one. Now I'm to the third slide.
Just wait, so maybe it will, some lag is there, so maybe it will come because it is showing us only a single slide only, the first slide only.
Only the first slide. Okay, I'm on the third slide, so it's not coming.
Yeah, maybe some connectivity lag may be there. So
It is
yeah,
okay.
earlier it was changing, but yeah, now change, sir. Now just keep on changing.
Second slide.
Yeah, now it is coming. Okay, sir, you can begin with that. No problem. Just come to back to your first slide. Yes.
Okay.
Now it will work. Please.
Okay, so thank you again. So the title of this talk is just to share some experience with some of the work that I've done. So on 3D printing and processing of bioceramics. Currently I've moved back from University Tenaga Nasional back to University Malaya. So I'm also now the Deputy Vice Chancellor at University Malaya. So just Ravi has given a rundown of my credentials. So very quickly, I just highlight some of the key credentials. So I have a PhD in advanced material, focusing on engineering ceramics, uh, which I've obtained in 1997, and Bachelor of Mechanical Engineering First Class, both from Sunderland, UK. All in, I have about 25 years of higher education, research, and consultancy experience. Currently, I'm a senior professor of mechanical and materials engineering at the Faculty of Engineering at University Malaya. I've served in many capacity in terms of administration uh, in between 2014 to 2018, just before COVID. So 2014 to 2018, I was holding the post of an associate director with the Engineering Accreditation Department, Board of Engineers Malaysia. So I'm one of my strength is on the engineering accreditation. So I've served quite a bit of time in bringing Malaysia into Washington Accord. To date, I have published over 350 papers. So it's a mix of ISI as well as proceedings. My H index based on Web of Science, I'm at 45 now. My Scopus H index is 65. I'm listed in the top 2% scientists by Stanford since 2020 right up to 2024. Currently, I'm also a distinguished professor with two university, Yunnan and also with NPU, Northwestern Polytechnical University. Both these universities are the double first class universities. So in China, they have close to 2,000 university, and they have various ranking. And these two universities are in the top, you can say in the top 1%. So they call themselves the double first class. So there's about 46 university in China that is in the double first class region. And I'm also visiting professor in many countries. A lot of awards I've won, funding as well, as mentioned by Ravi just now. I'm a fellow of the Academy of Sciences Malaysia and fellow of several other institutions, including the Institute of Mechanical Engineers UK and the Institution of Engineers Australia. I'm also a professional engineer in Malaysia, chartered in the UK, chartered in Australia as well. And over the years, I've expanded in terms of research. I started off with, of course, on engineering ceramics. So I developed engineering ceramics. I do a lot of formulation. In my early days after graduation, I was with a research institute in Malaysia. and part of my work is to provide consultancy services to the industry. So a lot of industry, especially mechanical related industry and cutting industry, they use a lot of cutting tool, metal cutting tool, stainless steel, titanium, and so on. So they have severe issue with wearing of these tools. And so I've developed in my early days a lot of engineering ceramics and composites to assist the industry in terms of replacing their tool from metallic based material to ceramic based material. So I spent a good 5 to 8 years in this government research institute where I did a lot of development work and a lot of commercialization. Subsequently, I've branched out into bioceramics, so where I've developed bioceramics, mainly calcium-based bioceramics for orthopedic and for clinical application. So I've done a lot of work. I have formulated my own material, my own hydroxyapatite, which can be used in bio application. I've also subsequently branched out into welding, laser welding. I have produced at least 4 PhDs in the area of laser welding and metal alloys, dissimilar metals. So I have strong collaboration with Harbin University in China, where we do a lot of laser welding. And I also look at failure analysis. This is another thing that I've picked up over the years. Once you are able to work on a particular material, you know how to use all the various instruments. So subsequently, it's easy to get involved into failure analysis. So I do a lot of consultancy whenever there's failure of mechanical parts and so on. They normally, this industry, they come to the university for help to identify the cause of failure. So so I do a lot of failure analysis as well, and also I look at the corrosion. I have some projects on degradation of materials and corrosion, and these include polymeric based material, metallic based material, and also ceramic based material. So I would say all in all, I have expanded, not just focusing on ceramics, but I've done many other work as well. I have also worked with colleagues in the area of heat transfer and nanofluids. So I have several publications related to this area as well. So I think as you grow older, you will expand your research capability. Okay, this morning talk, I want to talk a little bit about engineering ceramics and focusing more on bioceramics, the work that I spent a lot of years working on. Okay, when we look at the medical sector, we know that in the medical sector, when it started in the early days, a lot of alloys, metal alloys, stainless steel, titanium used. But over the years, researchers have developed ceramics, especially calcium based. One of the issue with metallic material is that once it is implanted, it will always be a foreign body. So it is biocompatible, but it is bio inert. It is not biocompatible with our skeleton structure. So therefore, researchers have looked at developing material, ceramic-based material, to work hand in hand with metallic-based material. So ceramics has been used a lot in the medical area, mainly because of its property itself. It's being inert. It is non-toxic. It's when in terms of hardness, it is quite hard. It has very good compressive strength. So what it means is that its wear resistance property is very good. It is able to sustain long time, and calcium based material can even fuse with the bone structure, so it can be permanent. So it can be a permanent implant in the skeleton structure. Okay, but one of the biggest issue with ceramics, as some of you all may know, it's the brittle nature of the material. It is good in compressive nature, but in tensile, it is quite weak. And therefore, ceramics cannot completely substitute metallic based implant. So we use ceramics to complement. Okay, so over the years, what researchers have done is to instead of use monolithic ceramic, that means a ceramic which is 100% based on a particular composition, they dope or they mix with other materials. So ceramic composites have been developed in order to mitigate some of this brittleness, but still ceramics in its actual nature form, it is brittle. All right, so a lot of these ceramic based material are used as coating on metallic implant, and therefore this complement the use of metallic implant, because the surface of the metallic implant will be ceramic based, which is biocompatible with the bone structure. The internal is metal, which will serve to sustain or carry the mechanical strength. So especially when the loading is in tensile in nature. All right, there are a lot of ways of how bioceramics are formed. Traditionally, or conventional method is through pressing, die pressing, whereby we develop a mold and we use powder to compress it into shape. And then after that, we eject the parts, and then after that, we subject it to subsequent processing like sintering and so on and so forth. Over the years, researchers have also developed injection molding ceramics, where there are machines that are being developed in order to allow, similar as plastic molding, injection molding, you can also inject ceramics in order to make parts. But again, the limitation is always with the brittle nature of the ceramics. You will always need to mix it with polymer, because with this sort of processing, you need to have a flexible stream of material, and ceramic in its own nature, it's brittle, so it's very difficult. Recent years, researchers have focused on 3D printing of bioceramics, and this 3D printing has its advantage, because it allows near net forming of structure. It builds layer by layer, just like the printing of when we talk about rapid prototyping of metallic component. So it's on a similar nature. 3D printing of bioceramics has been developed. So this material, this process actually creates an object by laying layers by layer of material, okay, until the full structure is formed. So it allows for complex and intricate design of components. Okay, and in principle, there are two major steps involved in printing of bioceramics. That is, first you need to model it using CAD software or any tangible software, whereby you create the layers, the structure that you want to form, and then after that you couple this model with the 3D printing machine, and then it will start printing according to the layer. So people have developed in China, for example, and I'm sure in India as well, people have developed their own 3D printers. So the 3D printers now is very common. People can develop. The challenge is always to find the right material, the right composition in order to make the filament, in order to print the particular object, especially when printing polymeric material is not an issue. You can buy, in fact, I think if you check online, maybe in Shopee as well, you will be able to find a polymer 3D printer. So the polymer 3D printer is cheaply available, but to print ceramics, it is not as straightforward as printing polymeric material. All right, so I talk about the two general principle, the modeling part. So you really need to develop that model, that the component that you want to make using CAD software or any animation modeling software that is compatible to your machine. And then after that, you use that, you build layer in the model, and thereafter you couple it with the machine, and you transfer, you convert the machine, the software code into a machine code, and it starts printing the particular material. All right. So during the printing, this is where you have a layer of powders will be laid layer by layer based on the model that you have developed in your CAD or your any animation modeling software that you have. Okay. All right, so there are two main common methods that are used for 3D printing of ceramics. So the two common is SLS, and SLS is one of it, and the other one is FDM, fuse deposition method. Okay, in the SLS is taking after the rapid prototyping. So here, selective laser sintering is where we use laser as the heating source. So the structure or the component that you want to make, it is being sintered simultaneously as the object is being printed using laser. So laser helps to melt the particular material, especially the ceramic material, at a particular temperature and deposit it onto the surface as it builds. Okay, so in the SLS, as the diagram shows, normally you have a powder bed, and this powder bed can be made out of any material, ceramic material that you want, whether it's a zirconia based or you want hydroxyapatite calcium based, and so on. And based on the powder bed, as the laser will take the of course the guided by the software, and it will start to melt the powder layer by layer. As it melts the first layer, the platform will move downwards. And so the powder, the free flow powder on the surface, on this side, on this section, will eventually goes down, and you have the layer being formed. All right. Or sometimes there's a roller that pushes the powder, because as you go, the powder gets less and you need to top up in order to allow more available material for the forming of the object. Okay, and that's how the principle of SLS. So the laser helps to, the intensity of the laser helps to melt the particular powder as the formation takes place. The other one that are frequently used for printing of ceramics is the fuse deposition method, or short form FDM. So here you need a filament. This FDM is the most common technique being used for most application, and there are maybe about 7 or 8 companies in the world, mainly in the Europe. They develop these FDM machines, and they are expensive. And the roll of filament that consists in this filament, it's a polymeric based filament. Inside you have ceramic powder. All right, so the polymer acts as the binder or as the carrier. You need to be flexible. All right, so this is normally comes in a roll form, in a roller, and this filament is put through a extruder, and as it goes through, it melts soften the polymer, and it creates the object. So depending on what object that you want, that you have drawn in your animation or your CAD software, so it will then make a run and make layer by layer of the object that you want to create. All right. In this case, in the FDM method, as compared to SLS, in the SLS, the component, once it is completed, it is already in a solid form. Consolidation has taken place during the laser melting. In the form of FDM, the object that we have obtained has not been sintered yet. So you need to subsequently put the component through heat treatment process. So you have to debind the polymer. Sometimes, depending on the filament being used, some of the polymer is still remaining in the structure. So normally we do debinding at low temperature, maybe below 500 degrees centigrade, and then after that followed by sintering. All right, so during the sintering, the particles will get consolidated, and then you will able to obtain the final product. So FDM is most common, as I said, about 7-8 companies in the world. In Malaysia, we don't have a company that develops the FDM for ceramics. We have a lot of FDM that is used for polymer-based printing. So polymer-based printing is not an issue. In fact, our one of my PhD students have even in China, he has even made the material, made the machine. So it's you can go to YouTube. In the YouTube also, there are a lot of channels that teach you how to make a simple printer. All right, so that you can print polymeric materials and so on and so forth. But for ceramics, as I said, the challenge is always with the filament. Okay, so in terms of bioceramics, when we talk about ceramic materials, ceramics, there are many classes of ceramic. There are the traditional, there are the advanced ceramics, and then there is the class of bioceramics. My PhD is not in bioceramics. My PhD, although my degree is in mechanical engineering, but I took a project related to using ceramic for mechanical application, and the focus is mainly for high temperature application and for a high wear resistance applications for like cutting and so on and so forth. So I developed during my PhD days, I developed zirconia ceramics, which I've used for cutting tool and so on. But subsequently, I branched into bioceramics. So these are class of ceramics that can be used in the human body for the replacement of disease or damaged parts. Normally, people get involved in accidents, and based on that, they break their bones or they crush their bones, and these bones can never be replaced in a natural form. It will take very long time, or maybe it will never be replaced, and therefore, in order to assist in the healing process, this bioceramics has been developed and being used in as a substitute. Okay, so to allow the heart tissues to heal, and especially calcium-based bioceramics, it allows infusion of the veins and the human skeleton structure. So there will be infusion, and therefore it becomes permanent. The body thinks that this bioceramic is part of the skeleton structure. Okay, so a lot of application for bioceramic as medical implants. So I've done a lot of work with in University Malaya. We maybe I should maybe some of you already know University Malaya. So we are top 60 in the world. We are a big university. We have 44,000 students. We have 12,000 staff, academic staff, about 2,000 to 2,500 academic staff. And we have two hospitals. One is a public hospital and one is a private hospital. And we receive more than 1 million patients a year in our public hospital. Okay, it's called University Malaya Medical Center. And in this center, in UMMC, we also have professors who do research, and I work with them to develop bioceramics, which can be used as implant. All right, so we can use this bioceramic for medical implants. So meaning that as the name implies, it's implant. So it's used in the body. It's planted in the body, and we can either use it as a solid bulk, if the application allows bulk component, or if it is not possible, if it has to be like, for example, for hip replacement, we have to use metallic, mostly either titanium or stainless steel. Then what we can do is we can use coating. We can coat bioceramics over the metallic implant to allow strong fixation when the ceramic come in contact with the hard tissues. Okay. So these are some of typical application. I think some of you all know that. So for hip replacement, especially total hip replacement, not THR. So where there is damage, as you can see, this is the original on my right side, as you are observing. So this is the original femur. You have the femur bone, and this is where you have the part of the femur that goes into the pelvic. As we grow older, our bone gets porous. Okay, because this is a natural way of how human body extract calcium. Okay, from to keep the body alive. As we grow older, the ability for our digestive system in order to extract calcium from food lowers. So the body gets lazy. The system, our system gets lazy, and so if the body don't need strength, it will extract calcium from the bone, and for that as we get older people, and especially with your weight, there will be fracture. Your legs will not be able, your femur will not be able to sustain the weight, you know. So as a result, it may break. And once it breaks at the neck area here, so there is no more connection between the pelvic, the upper body, and the lower body. And as a result, we need to make sure there is connectivity. And the way how it's being done is really to implant a metallic stem into the femur part, which normally it looks something like that. You have the stem, a metallic stem, and you have a head, a round, almost a full head that goes into the pelvic side. So the orthopedic will have to do some reconstruction in order to allow a metallic ball to sit inside and allow the rotation in the 360 free rotation, so that the legs are attached back to the pelvic, and to allow motion, walking, and so on and so forth. Okay, so as you can see, normally the part that goes into the femur, so this metallic part, so this part can be coated, in order to allow good bonding between the bone and also the stem. And the head can be made out of metallic, or it can be made out of ceramic. Researchers have done a lot of work in this area, and they find that ceramic versus ceramic. So on the head, on the cup side that goes into the pelvic, and the head side. So when you have ceramic in contact with ceramic, the wear rate is very low as compared to polymeric material, or you have a metallic material. So this is where one area where ceramic is being used. The stem cannot be made out of fully ceramic, because the pelvic, the femur will be subjected not just compression, but also will be subjected to tensile loading. As we walk, there will be tensile loading, and that may cause fracture of the stem. So as a result, it has to be made out of metallic based material. So normally it's either stainless steel, or it can be titanium. So it's typically, as you can see, this stem is being coated with ceramic base or bioceramic. All right. The typical application of bioceramic is for knee replacement. So in the Europe or in the US, there's a lot of people that are overweight, and as a result, at a young age, they tend to either break their hips, fracture their hips, or they have problem with their knee, where it requires the replacement. Okay, you need to put an artificial knee there, and the component of the knee, as you can see, can be made out of ceramics, whereby the two part, the femoral component and the tibial component, the bottom component. So they both can be, typically it's made out of metal, but it can also be made out of ceramic, because for the knee, it is more compressive in nature, and therefore ceramic finds, bioceramic can be used for those two applications. And normally it is made out of either alumina or zirconia. Not hydroxyapatite, because hydroxyapatite don't have the toughness as required for the application. And of course, we will always have a polymeric PE, a polyethylene, that helps to cushion the effect between the two sides. So very famous in the Europe, there's a lot of people that get knee replacement, and also in hip replacement. In Malaysia, I'm not sure about in India, but in Malaysia, we also have this hip replacement, but not as high. Percentage is not as high as in the America and in Europe. Okay, so we use, as I mentioned, the bioceramic calcium-based phosphate material, that is HA, stands for hydroxyapatite, and TCP, tetracalcium phosphate. So these are the two calcium-based material that are frequently used as coating material on metallic. So it allows osseointegration, means that it allows the natural tissue to integrate firmly with the calcium base. And once infusion takes place, it becomes permanent. All right, so it helps with rapid bone formation. If the patient is young, the possibility of fully grown bone to take place within the lifespan of that particular patient is possible. But if for older patients above 50, 60, the fully replacement of the artificial bone or the hydroxyapatite with the natural bone may not take place. But again, HA being calcium based, it tends to fuse together with the bone structure, so it allows uh, good integration, and patient will not the body will not think that it's a foreign body there. All right, so coatings are also used onto metallic, so it allows that osteointegration to take place. This is another example of a TCP. This is basically done by printing, by 3D printing. So we have a porous TCP that mimics the uh, uh, like a spongy tissue in order to help the area where it is damaged, in this case for jaw. Okay, when the patient gets involved in an accident, so there is a fracture, so it allows the cage holds the spongy calcium based material to act as a filler, and over time the osteointegration between the bone structure infuse into the tetracalcium phosphate. Tetracalcium phosphate, it does not stays permanent. It gets absorbed slowly by the body, and so it serves the purpose as a filler, and eventually it gets replaced, hopefully, if the healing is good, depending on the patient. So it's not our body is quite complex. So some patient they heal better than other patient for similar application. So this acts as a filler. It allows that integration to take place. So normally the cage is made out of a ceramic based material, so like a zirconia, and this is 3D printed as well. All right, and inside you have the spongy tetracalcium phosphate that helps to allow the growth of the new bone. All right, and for skull implant as well, when especially for cancer patient, when they have cancer in the brain, and in order to remove the cancer, the doctor normally they will have to cut through the skull, and for that there will be a hole being created, and thereafter, in order to protect the soft tissues of the brain, in the past metal is being placed over the section where it's being cut in order to protect, but these days we can use bioceramic because this area will not be subjected to loading. All right, so obviously once someone have its part of its skull being removed and being replaced by a bioceramic, the person cannot have a active spot life. All right, so because of course with hydroxyapatite has the strength and the hardness in order to protect, but obviously for example to play football and so on, it's not advisable because it can crack when the patient hits the ball and so on. So normally it is used only to protect the soft tissue of the brain to allow healing to take place, and this remains permanent there. So with hydroxyapatite, the good thing is that once it is being put in place, fusion can take place at the connection between the hydroxyapatite and the skull structure. Okay, so that's one area where HA has been used. In the University Malaya, we have surgeons that work on this material, and I work closely with them to use bioceramics for this purpose. All right, bioceramic can also use as dental. All right, and this is something that I have worked with one industry in order to develop the artificial implant. So for orthodontic devices, for braces, prostheses like crowns, bridge implants, like all ceramic implant, and so on. So this is very common these days. If you, especially adults, we know that once we lose our tooth, we will never be able to have a natural tooth. So we will need to replace it with an artificial implant. All right, and so ceramic serves very well in this particular section. So I mean, you can also use titanium. In the past, titanium has been used, but these days ceramic has been used. For example, if you look at this diagram here, we have an all ceramic implant. So you have the post that goes into the jaw. It is made fully out of ceramics, and then after that, even the head, the tooth can be made out of porcelain or can be made out of zirconia. All right, so it depends on what the patients want, and since the application is more of compression, so all ceramic dental implant works very well. All right, so obviously there are also titanium implant where the implant can be made out of metal, but the head is made out of ceramic. All right, so that's also possible, but the only problem is with the implant, metallic implant, when it is being screwed into the jawbone. Over time there will be effect of loosening because the metal is very hard, and therefore it will cause wearing of the bone structure. All right, over time when the patients bite and eat and so on, so there will be movement, and therefore after certain years there may be a need to replace the stem to use a bigger diameter stem. All right, because of the loosening of the stem. But with all ceramic implant, it tends to allow osteointegration to take place, especially if it is made out of hydroxyapatite, or the area or the stem is being coated with hydroxyapatite. So it allows good fusion, good interlocking with the jaw material, bone material, and therefore it binds well. So it keeps it in good position. It holds it in position, and therefore you won't have this loosening effect. So that's why a lot of people opt to use all ceramic dental implant. All right, so I don't have a dental implant. Hopefully none of you all will need that as well. But of course, when that happens, when you lose your tooth, especially in the front side of your mouth, then obviously you would need to put an implant so that you will have back your self confidence and so on and so forth. For braces, we have metallic braces, but with combination of ceramic as well. So that's also possible. And the good thing about ceramic is that the material can be, especially for the head, for the tooth can be developed by just adding can be processed by adding certain additives to change the color. So if you have a brown, very brown tooth, the tooth, the artificial tooth can also be colored, can be developed or processed by adding some additives so that it matches your original tooth. So that's the good thing of it. I have some crown. I have crown. So this is a crown. I have two crown. I had a root canal. Not root canal. Yes, a root canal. So two of my on the inside. As a result of the root canal, the tooth needs to be crowned to be protected, and therefore the dentist is able to match the color. So I have one porcelain and one zirconia inside. All right, so as a crown. All right, so these are some other application. Ceramics are being used for many other application as well. I just moved this aside. All right, so for cranial repair, for skull, for dental, for even for artificial heart valves, there are some work being done on trying to use artificial ceramics as an artificial heart valves, where they put it into the artery. And of course, for load-bearing application, we have seen this for hip replacement, of course, knee replacement, and the other one is calcaneal repair. So at the part of the feet, and this is very prone for accidents, where especially those on the motorbike. Like in India, I know in India your main transport is using motorbikes. In Malaysia as well, we have quite a high percentage of people still use motorbikes to get from one point to another point, and motorbike accidents are very high in Malaysia. I'm not sure in India, but in Malaysia it's high, and there are many cases where the rider would fracture the feet area, the calcaneal area, and as a result, a lot of metallic implants are being used in order to hold the bone together for healing to take place, and so on and so forth. So these are some clinical uses of bioceramics. Okay, so there are mainly three types of bioceramics: bio-inert, bioactive, and bioresorbable. So when we talk about bio-inert, means that it is completely inert. It does not take place. It does not have any chemical reaction with the body. When we say bioactive, there are some chemical reaction whereby osteointegration can take place. All right, so there are integration when we say bioactive. When we say bioresorbable, what it means is that it is there for a temporary period, and thereafter it gets absorbed by the body, like TCP, tetracalcium phosphate, bioresorbable ceramic material. So these are the three classes of material. And why hydroxyapatite has been used is because when we zoom into our, or on a micro or nano scale, when we zoom in into our bone structure, all right. So this diagram shows when we zoom in, we will see that the crystal that makes up the collagen fiber right inside our bone, it consists of crystals of hydroxyapatite. And that's how researchers realize that if we can develop artificial calcium phosphate based material, the body will accept that particular ceramic. And that's how, based on the understanding of the bone structure, hydroxyapatite has been developed and being used very widely. I have a patent on chemical processing of HA, whereby the HA that I developed can be sintered at very high temperature and can also be used for microwave sintering and so on and so forth. When we talk about hydroxyapatite has to be bioactive, meaning that it is there permanently. So it is not like TCP. So some application that we use this bioceramic, especially calcium based, we want the calcium based ceramic to remain permanent for reasons that because the body will not be able to grow new bone. So we want to have a permanent filler. And so hydroxyapatite is being used. But there are applications where we use TCP, tetracalcium phosphate. All right. So that means it is not purely hydroxyapatite. It has a dual phase structure. It has a TCP, alpha or beta TCP in combination with HA. But when we talk about HA or hydroxyapatite, it is purely HA. So that means it does not have other secondary phase. So it is purely monolithic 100% hydroxyapatite. And during processing, when we sinter, hydroxyapatite can undergo phase transformation into calcium phosphate into TCP. So some percentage of the hydroxyapatite crystal can be transformed into TCP, and that becomes an issue if we use hydroxyapatite as a solid implant, because what will happen is that over time, part of this TCP will get leached into the body, get absorbed into the body, and therefore the component loses its mass, and it can fracture. All right. So when we develop hydroxyapatite, we always need to check its ability to withstand high temperature, especially during sintering. And the material that I developed can withstand high temperature as compared to commercial material. So we have done a lot of comparison and testing in order to look at the the quality of the HA that my lab has developed. Okay, when we talk about processing, we can categorize the processing into two main methods. One is chemical route. The other one is fully conversion. That means we convert directly. We use biogenic waste material and convert it directly, most of the time through heat treatment, into hydroxyapatite. All right. So all other methods, really, it's the chemical route. It's either the dry method. Dry method, there are two, either in a solid state way where we react two different material together. We heat treat them, and the outcome, the yield, is hydroxyapatite. Or we can use a mechanical chemical method where we react, and with the assist of mechanical rotation to cause some agitation for the reaction to take place, and the yield, after we clean the byproduct, we'll get the yield as hydroxyapatite. Then we have the wet method. The wet method, when, as the name implies, it is done under wet conditions. So normally it's the famous one is chemical precipitation, where we react calcium-based material in a liquid form. We react with phosphate-based component also in a liquid form. So we mix them based on some process, and the yield will be hydroxyapatite. Okay, there's the hydrothermal technique, there are hydrolysis technique. Among these three techniques, the chemical precipitation allows the researcher to develop a large amount of yield as compared to hydrothermal and hydrolysis. And then of course we have the high temperature method, which is combustion or pyrolysis. So this high temperature method is good for research. So for research, it's nice to do this technique for publishing papers and so on and so forth. But most of the hydroxyapatite that is available in the market, it is developed through the chemical precipitation method. All right, so chemical precipitation, it's easier, easy to control, and you can scale up. So it's easy to scale up as well. All right, so these few slides show the principle of each of the techniques. So I'll go a bit quickly. So the mechanical chemical method. So basically, because the mechanical means that there is a mechanical assistance. So like ball milling or planetary mill, and this through this milling through a mechanical form, that means rotation. Electrical energy convert into rotation energy. So through some mechanical device which allows the rotation to take place. So that allows the reaction to the chemical reaction between the agents that we use in. So a calcium agent and a phosphate agent, typically calcium carbonate and dicalcium phosphate being used. And during this mechanical chemical process, the mechanical chemical process takes place, and the byproduct will be hydroxyapatite. And then we also have the chemical conventional wet method. So when we look at the wet method, so this is very straightforward, the chemical precipitation method. I am one of the early pioneer in this chemical precipitation method. So this been done for like almost 20 odd years, 25 years ago. So it's very simple. All you need is a calcium agent. So most of the time we use calcium hydroxide. We mix it in liquid. So we dilute calcium hydroxide into liquid, and then we take phosphoric acid, we dilute it in liquid, of course, as at a certain ratio. And this is where the challenge come in, how we control those ratios. And then we use a precipitation method where we have the calcium hydroxide being placed in the beaker. It is being stirred by a magnetic stirrer, and we titrate, or we put the phosphoric acid, we titrate it into the beaker that contains the calcium hydroxide, and we control the whole process. We monitor the pH, we monitor temperature, and so on, and based on that, we are able to obtain hydroxyapatite. And then thereafter, we clean we clean the particular reaction, the byproduct, and after washing, after that we filter it, and then we dry it and we obtain the hydroxyapatite powder. And this gives quite good yield. So I've done most of my work. We use the chemical precipitation method. So we develop that and we buy in commercial powders and we make comparison in order to see how good is the powder that we develop in the lab. All right, then there's also microwave assisted hydrothermal method. So researchers have used, instead of using normal hot plate, they develop in such a way there is a machine where there's a ability to induce microwave. So microwave allows the reaction to take place when the two mixture, when you have the calcium based liquid solution mixed with the phosphate based solution, and you pass through microwave, so you heat up the liquid, and that causes the formation of reaction takes place, and subsequently you get different product depending on pH. So I mean, it's you need to control the environment. Once you control environment, most of the time it is the pH that we can control. So for different pH you get different morphology of HA crystals being formed. All right, so pH 5, this is typically reported in the literature. I've not done the microwave assisted hydrothermal method. I have always stick with the chemical precipitation method because I find that based on the readings that I've done, the chemical precipitation is much more superior in terms of the yield, the reproducibility, in terms of quality. Rather than using all other technique. All other technique is good to publish paper. You do a little bit of mixing here, change a bit of parameter, you can write good ISI papers. You know, you get nice structure and then you can publish. But for application, I think it's a bit difficult to scale up. All right, to scale up in order to control the required morphology. All right, then you have the solid state method. Solid state method, very straightforward. Mix two items together, put it in a furnace and wash it. You get the hydroxyapatite powder. So that's the solid state method. Then you have the combustion method. This I have done, combustion method, using the fuel. We call it fuel. We use glycine. So you mix calcium nitrate with diammonia phosphate. You can try it in your lab. There's no but of course at a certain ratio, you got to keep the ratio of Ca to P of 1.67. So you need to work out the amount of ammonium phosphate versus the calcium nitrate. You mix them, and thereafter that you either put it in on a hot plate. Normally it should be in a stirring condition on a hot plate, and you pump in nitric acid or glycine for that fact as a fuel. And as the product dries up, as it dries up, you will get a combustion, and through that combustion, you after the combustion, the product that is produced from that combustion, you will get the HA product. But it's difficult to control in terms of properties, in terms of yield. You get very little yield when you use this technique. But as I said, for research, for the purpose of doing a PhD, for master's research, fantastic. I mean, you get quite a good results. You can play about with the parameters, and you get different morphology, different properties. You look at you sinter them and then you test them, and then thereafter you put it for biocompatible studies. So you get a lot of results. So it's nice for publishing papers. So a lot of people have used this technique mainly to publish, and they make some comparison showing the viability of combustion method. All right, so these are some of the issues with the chemical route. Remember, just now there are two routes that we can produce HA. One is chemical route. There are some issues with this route. So some of the issues is that the purity of the HA itself through the mechanical chemical process. Normally the powder produced from these techniques, even for the chemical precipitation, they are not highly crystallized. All right, so subsequently you need heat treatment to obtain a highly crystalline material. You also have problems with agglomerates with this chemical route. As I mentioned, that's always the challenges. instability of the hydroxyapatite itself. Like just now, you saw different structures. Some look like a star, some looks like a rod-like, some looks like a spherical powder, that kind of thing. Normally, we find that the rod-like structure is more stable than the looks like a star, or in a form of a round circular particle. So the rod-like seems to be very stable. All right, but again, depending on how you process them, you get different morphology, and that will influence the stability of the hydroxyapatite phase when you want to heat treat or when you subject it to sintering. Okay, and then sometimes you get secondary phase calcium phosphate formation, like tetra calcium phosphate TTCP, or even calcium oxide being formed. So these are considered impurity, although the body can accept TTCP or CaO, calcium oxide in the body. But when you use for implant, a solid HA implant, remember I said earlier that we want the implant to remain as implant for a long period of time. But once you have degradation taking place, HA transforming into secondary phase, it causes an issue. It loses its integrity. All right. So as a result for this, people look at the other option is to convert biogenic waste material. And biogenic waste material normally is using animal bones. All right. So we use animal bones and then we convert this bone directly into hydroxyapatite. And people have looked at various biogenic source. All right. Biogenic source like cows or bovine. Of course, they look at pig, fish, chicken, and so on. Even they use sea items taken from the sea, like shells and so on, and in order to see subject it to various processes and see if it can be converted directly into hydroxyapatite. All right, and there are several process involved in the extraction of this calcium from the animal bones. Okay, so extraction of minerals from bio waste products. So a lot of this, sorry. Okay, so basically we extract. All right, so this is an extraction process. I've worked with chicken bone. I have done the other one with eggshell. Eggshell is one of the easiest biogenic source that you can convert because eggshell is calcium carbonate, and you burn the carbonate away, you get pure calcium. So through using eggshell, you are able to develop pure calcium, which then can be used as the main one of the main ingredient in order to make this hydroxyapatite. Okay, so there I work with bovine. I've worked with bovine as well. I've worked with not pig. I've not tried pig bones because from research that have been done, it seems that the pig and chicken. I've tried chicken, but chicken bone is too soft. And the byproduct, the product that you obtain, the hydroxyapatite that subsequently that you make out of the chicken bone, it does not have very good mechanical properties. Fish bone, also the same. It can be a good calcium source, but the subsequent processing making into hydroxyapatite, when you test the mechanical properties, it is not as good as using eggshell or bovine bone. All right, so eggshell synthesis from eggshell. So a lot of my work has focused on using eggshells, whereby we crush the clean and we crush the eggshell, we burn the calcium carbonate away, and we get pure calcium. We calcine them. It gives out a very terrible smell when you burn eggshell. So you need to have a proper enclosure extraction when you burn eggshell. And the byproduct is a white color powder, and that powder is pure calcium. All right, and then subsequently you subject it to the normal chemical processing, mix with some phosphoric acid and so on, go through the chemical process, you will be able to obtain HA product. All right, so synthesis from eggshell, so very straightforward. And then of course you can use the shells. So this is another method that has been used, but again it is more for research purposes, because the issue of the yield and the method, the technique involved. All right, so sometimes some of these techniques uses chemical, toxic chemicals. The byproduct of the chemical are toxic, so therefore it is not viable for scaling up and so on and so forth. So we can use marine organism in order to convert that use their convert their calcium into HA product. So that's possible. So these are some of the two things. Oh, that's the sorry. All right. So from biomolecules, we use plants. So plants is also possible, but the yield is very small. There are some work being reported, but as I said, it is good for writing papers lah. So using papaya leaves, the orange peel skins, egg white, potato skins, and so on and so forth. So all these are good for research and writing papers. Okay. All right, so microwave assisted eggshell derived. So this is something that I've done. I spent a lot of time, produced a lot of PhDs in this field, in this area. So we use microwave instead of the conventional heating. We use microwave, and microwave is very rapid, and the product that we got is in the nanoscale. So basically, through a certain processing, after we obtain pure calcium, we subject it to a process where we use microwave as the energy source. For a very short period of time, we are able to produce HA powder, and this powder subsequently through the various tests that we have done, they are superior in nature and can be used for all sorts of components. All right, so these are the powder. As you can see, this is the HA powder that has developed. We produce nano powder, so they are mainly rod-like powder. And this is the microwave of the nano powder that we have developed in the lab. And this is the enamel of a human tooth. So this is actually my tooth. Some years back, you see, if you read papers, most of the time when they report, they always say that the HA powder is compatible with bone, but they don't show. Most researchers will not show the comparison of a typical human bone X-ray XRD pattern with the artificial powder that developed in the lab. And of course, it is unethical to take human bone and do an X-ray on a human bone. So one day I had a problem with my wisdom tooth. That was sometime years ago, maybe about 10 years ago or 15 years ago. I had a problem with my wisdom tooth, and while my tooth get extracted, I was at that time thinking of the work that I was doing. And when the dentist throw the pieces of the tooth into the beaker, I looked at it. I said, hey, I told the dentist I would like to take the tooth. He said, okay, it's up to you. So what I did was I grind the surface and I done the X-ray. So the whole idea here is really to show the similarity in the pattern. All right. So I published this already. The similarity in the pattern between the powder that I developed and the natural HA. All right. So the enamel is purely calcium, so it's hydroxyapatite. So as you can see, it resembles, okay, good resembles between human tooth and the powder that I developed through microwave method. We also have done implantation in rabbits. So this is a tibia of a rabbit that we have implanted the microwave HA. As you can see, this is the block of HA that we put into the tibia. So this is implanted. So after 6 months, the rabbit is being sacrificed. The researcher, they observe the healing, and there's no reaction at the part that they have done the insertion. So it heals very well. And after 6 months, when we want to extract the hydroxyapatite, it was difficult to identify which one is the HA, which one is the bone marrow. And this diagram, as you can see, So this is the HA that we have implanted inside. So this is a cross section when we implanted in. And you can see very good osteo integration between the bony structure and the surface of the hydroxyapatite. All right, so why we use microwave? Microwave, as you know, is rapid. You every day use microwave at home to heat up food and all that. So within minutes, you can really heat up. Comparison I've done as comparing microwave versus conventional. The time taken, okay, one is the time taken is very short. The other one is the energy. Because the time taken is short, therefore the energy consumed is also very low. Here's some study carried out by Professor Sato from the National Institute of Fusion Science in Japan. So he has done the comparison in terms of the processing time to process alumina ceramic versus conventional. So he have done so for microwave is just 20 hours as compared to 96 hours for conventional. This is for sintering purposes. The energy consumed, obviously less hours you use, less energy you use, and of course the cost, because the cost is related to the energy usage, so it's cheaper. Okay, 1/6 cheaper, 110 lower in terms of energy consumption, 1/5 lower in terms of the time to process alumina ceramics. All right, so rapid heating, this is a profile. This is for typical profile for hydroxyapatite that I use in my lab. I have an industry scale 6 kilowatt microwave furnace that is still functioning in my lab, and I've done a lot of work using this microwave. In the early days, I used to use the household microwave. Do you know that with the household microwave with proper insulation and a little bit of modification, using the household microwave that is the 1200 watts rating or 1500 watts rating, you can actually get temperature as high as 700 800 degrees centigrade. All right, so but you need to do proper insulation and so on and so forth. So as I said, for research purpose it's nice, but of course for commercial you would need a proper microwave furnace. So I have a proper 6 kilowatt microwave furnace. So it's a big furnace which we do a lot of microwave work. And this diagram shows the time taken. So it's fraction of less than 45 minutes. You are able to obtain hydroxyapatite that has similar density as the one that is sintered conventionally, which typically takes more than 24 hours. All right, so this is some principle. Microwave basically it is when we look at the differences in terms of the heating mechanism. So it's volumetric heating. Microwave is volumetric heating. Once every particles receive the energy, it starts to create heat, as compared to conventional, where heat is transferred from the outer surface onto the inner surface. So it's through a radiation convection process. So that takes time. All right. So the outer body will always be hotter than the inner body. All right. And that also create inhomogeneous structure and so on. But microwave, it is homogeneous because heating takes place in every layer simultaneously. All right. So that's the two difference between the microwave and the conventional. So of course we need the material to be able to couple microwave. All right, and this is the challenge when we want to microwave ceramics, because not all ceramics are able to couple microwave at low temperature, at room temperature. All right, so they couple very well when reach a certain temperature, most of the time above 200 degrees centigrade. So sometimes we need to have we use susceptors to heat up the area. We use susceptor like silicon carbide. Silicon carbide couple microwave almost instantly, and it heats up very quickly. So when we put susceptors like silicon carbide surrounding the sample, the surrounding area temperature will goes up very quickly. And once it is at the right temperature of above 200 degrees C, then the material will start to couple microwave, and it will start to then heat up continuously. All right, so that's some of the challenge with sintering ceramics using microwave. All right, so some examples of processing of microwave. So alumina, one of the thing with alumina, as you know, alumina needs to be sintered at high temperature for a very long period of time. As a result, you have grain coarsening. When the grain gets bigger, you lose the mechanical strength. All right, so this is the issue, and the challenge with sintering of alumina is really to minimize grain growth so that you have higher mechanical properties. So this is typical, showing the structure of conventional sintered, where if you work with alumina, it is not possible to get high density at a low temperature of 1350 holding for 2 hours. So this for 1350 2 hours, the density is about 65% dense. All right, and the structure is porous. But on the same count, we find that when we compare with microwave, keeping the time same, 120 minutes at the same temperature, 1200. All right, now in this case different temperature, this is higher, this is lower. So for the same condition, except for lower temperature, the density is already 95% dense. All right, so we can see that there is advantage of using a microwave to sinter alumina. All right, so this again just to show the variation in the grain structure. So as you can see, 2.37 micron for the same for the same okay. So for the same relative density, as you can see, when we look at the structure, structure at 70% dense, you can see that the one with microwave is below 1 micron as compared to the one that is conventional, way above 2 microns. Okay. For zirconia as well, we have done a lot of work. You can keep at low temperature for as low as 2 minutes. All right. We are able to obtain 97% dense, 98% dense with a average grain size of about 0.15 microns. So this is another work that I've done using microwave. So what we did was you know that if you work with zirconia, it is not possible at 1100 degrees centigrade to get at least 95% dense, right? So part of this PhD work was to try to enhance the low temperature capability of zirconia. That means the sintering capability. So what my student have done is that to dope zirconia with copper oxide. So with copper oxide doping, if we focus at low temperature 1100, beta doping, it is at about 57% dense. With doping, copper oxide doping and sinter at 1100, my student able to bring up the temperature, the density from about 57% right up to about 70%. All right. Now, when he used the same material, that formulation with copper oxide doping, when he couple it with microwave, it can go right up to at 1100 coupled with microwave for 1 minute, we can reach 95% dense. All right. So as you can see that microwave has that ability to increase or enhance densification of zirconia at very low temperature of 1100 and within a very short period of time. These are some example when the ceramics are fully dense, they tend to become transparent. So these are some examples. These are examples not from my lab, but from my collaborator, Professor Dinesh Agrawal from Penn State. So he is our professor icon, and he works closely with me in the development of this microwave, because his group is the pioneer. I think those who are familiar with Professor Dinesh Agrawal, he has just retired from Penn State. So he doesn't do much research these days, but I'm still in very close contact with Professor Dinesh Agrawal. So these are some of the pictures that he has sent that he has done on various different ceramic material. All right. So as you can see, they are transparent. All right, so these are spinel. These are hot press spinel. These are aluminum nitride. And this is hydroxyapatite. This is my HA. This is my the HA that I've developed in my lab, subjected to microwave at 1100 for 10 minutes. And you can see this is the sample. It is transparent and it is fully dense. These are comparison of some of the properties. So I circle here, as you can see, as compared to bone. Of course, with microwave HA, our bone density is lower than the HA. HA typically fully dense is about 3.156, 157. So grain size depends on our processing, about 0.2 microns. These are some of the mechanical properties. So if you look, compressive strength can go up to about 900 megapascal, bending strength up to 250 megapascal, tensile up to 120. So hydroxyapatite, they quite weak in tensile loading as compared to the bone. And Young's modulus is very, very high. And this is one area that we must take care of, because if we put an implant where the maximum load is undertaken by the implant material and not by the natural bone material, eventually the natural bone material will get weakened. Our bone structure needs to be subjected to loading. If it does not subject to loading, it tends to lose its calcium. And that's where, as I mentioned earlier, the body thinks that when you don't exercise, that's why as you get older, you need to really do a lot of exercise, because you should not allow your body to think that your skeleton structure do not require the strength, and therefore the body will extract the calcium from the skeleton structure. So if you active in sports, that send the signal to the body that you need to have strength in your bone, and therefore the body will have to work hard, your system will have to work hard to extract calcium from the food rather than taking it from the bone. Okay, so these are other properties. So just to compare, microwave in 30 minutes, at 30 minutes at 2.45 gigahertz, as you can see, as compared to conventional sintering at different temperature, you can see it is much better in terms of densification. All right, conventional is done for 24 hours, microwave is done for 30 minutes at the same temperature. So you can see the improvement there in terms of densification. So this just to show the similar thing, in a table form. I think what I want to highlight really, if you look at 1000 degrees centigrade with conventional sintering, it takes, in order to get a relative density above 90%, it takes about 1000 minutes, as compared to microwave. To get above 90% dense, it takes only half an hour. All right, so the advantage is there. So these are some diagrams, that some figures on the microstructure, but because I can't show it in the PowerPoint mode, it's not, you are not able to see. But yeah, as you can see here, this is very large by conventional HA sintered. You can see 10 micron as compared to this 2 micron. So the difference, as you can see in the scale form, they are different magnification. All right, different magnification, but the scale tells you the in terms of the microstructure. All right, so grain size wise, if you can see, a fourfold reduced by fourfold as compared to conventional. When you talk at comparison at 1300, you can see that. Okay. All right, so zirconia, that's on hydroxyapatite. So we also work on zirconia. So zirconia can exist in 3 structure. Monoclinic, normally in the powder form, and then you have, as you heat up, it goes into tetragonal and then cubic, and on cooling it transforms. This is for pure zirconia. So this is the polymer of the transformation that takes place. All right, so in order to stabilize, in order to ensure that the reverse transformation does not take place, normally pure zirconia is not used in its form. It is normally being doped with stabilizer like yttria or cerium oxide or magnesium oxide and so on. All right, so this is in a pure form. It is not being used because on cooling there is expansion. From tetragonal converting back to monoclinic, there will be expansion. As a result, there's severe cracking. Okay, so normally for biomedical application, it is the tetragonal zirconia polycrystal, TZP, or why TZP. Why means it's the stabilizer. It's being stabilized by with 2.5 to 3 mole % yttria. So with this stabilizer, you are able to retain the tetragonal structure at room temperature and therefore the highest mechanical properties. All right, so this is some comparison of YTZP, the tetragonal zirconia polycrystal, with some typical metal. And as you can see that the Young's modulus of zirconia is YTZP is almost similar as steel, and that's why YTZP is sometimes known as ceramic steel. And we have done some work on microwave of zirconia, and these are some of the comparison, conventional versus microwave. Okay, I don't know if I can play this. Let me try. Can you guys see this?
Yes, sir. Yes, sir.
Okay, some of the application, grinding media, sleeves, pump face, hip replacement, knife. This is a cutting tool that I've developed for commercial purpose, and of course for dental implant. Okay, so we have also made porous zirconia. This is for a company that where I'm a consultant with Best Tool Manufacturing in Thailand. Can you guys see this figure?
Yes, sir.
You can see this, huh? Okay. This is another work that I've done. These are drill bits. These are zirconia drill bits that I have developed together with the company in Thailand. So I'm a consultant for this particular company. And what this company have done is to make ceramic zirconia cutting tools for drilling purposes for dental to replace the metallic. Our tooth is very hard, and during replacement, using the metallic tool, it wears off very quickly, and therefore this company developed the zirconia drill bits in order for use for dental application. So I help them with the processing part in order to identify the best condition for sintering of their tools and for selection of material, and also for some strategy on how to enhance their mechanical properties. So these are other tools that have been developed by the company in Thailand. And that's it. Right. So I think I've taken enough time. So a lot of my work are really focused on developing this particular ceramic material for mechanical base and for biomedical base application. All right. So thank you very much for listening. And if there's any question, I'd be happy to answer. Thank you.
Thank you so much, sir. It was a very amazing session throughout and very learningful and insightful. So I hope that our participant will definitely get benefited out of it, and lots of aspects about the various the ceramics, biocompatible ceramics, and having their versatile applications in the domain of manufacturing as well as biomedical domain. So some of the queries also been written in the chat box. So while using PVA HA with ceramics, uh, what about the role of like viscosity and nozzle flow process? Any difficulty you have
Yeah.
faced? Yeah.
Well, I mean, like PVA, when we add, you need to look at the amount added, because most of the time we add the PVA as just as a binder, especially when we want to do pressing and so on, and we use a very small amount, and that needs to be quantified because it depends on the ceramic material. So sometimes you add in a certain percentage, and you will have to carry out some binder burnout cycle in order to see how well the binder is being burned out. Because sometimes when you put too much of PVA, normally less than 5%, that's what we normally add. Depending on the powder, as I said, some of the powder you need to have PVA. Some of it you need to add in a small amount of PVA, but you need to burn them out. If you put too much, then you create porosity in the ceramic. So yeah, some study needs to be carried out. But if you are doing slip casting, of course, when you do slip casting, then it's different. Then you need to carry out the rheology study in order to understand the behavior of the fluid, the amount of ceramics material that you put in, and the amount of deflocculant that you want to use, or if you use PVA or any other chemicals that you put in, then you need to quantify the ratio in order to ensure that if you are using it for slip casting, the flowability, the fluid are able to flow well into the mold, and for the particles to stick onto the wall of the mold in order to obtain the object and so on. So it depends on application, whether you use it in a dry form or you use it for slip casting or injection molding. So if slip casting, injection molding, yes, you will then definitely need to undertake study to understand the flow behavior of the ceramic when you mix with those polymer binders and so on.
Okay, thank you, sir. Another query is how to test osseointegration after making an implant specimen. Can you recommend some of the standard tests available?
Okay, so basically, I think for this biocompatibility, normally once you implant them, it's difficult. I mean, there's no really test that you can say there's biocompatible. What researchers have done is that they do it during animal study, like the one I showed you just now, the tibia of the rabbit. So when you develop the material before you implant, you would undergo various experiments, and one of it is the animal study. You do in vivo or in vitro study, and that will give you a good indication of the ability of your material to sustain once you place it in a human body, right? So that during that time when you do the in vivo in vitro, you would look at osteointegration. If you plant it in the animal, you would look at the bonding and so on and so forth. So that is the time that you do the evaluation. Once you implant into the body of a human, you are confident that the osteointegration will take place. And then, of course, the monitoring done by the medical side is to check time to time. They do X-ray in order to see how the fusion of the implant within into the bone, and to see if there is loosening. You will see the gap, and then
Thank you, sir, for this discussion. So another, I think it is the last query about
yeah.
for tooth printing, which polymer will be the best and what percentage we can take HAP?
For what?
What percent for tooth printing with HAP, which polymer will be the best?
Oh, for you mean to get a different color of the tooth? You mean?
Yeah, maybe he's just trying to ask.
Yeah. But normally for that we don't do painting. It's not painting, but it is already mixed in the formulation. So, for example, if you add in a little bit of iron oxide, depending on the percentage, very small percentage of iron oxide you add in, the ceramic will change from white to brownish, to brown color. All right, so it depends on the oxide that you add into the mixture. It is not not onto the surface that you do painting, but it's already being mixed. Normally they use iron oxide, very small quantity of iron oxide, in order to have the variation in color. Because our tooth, mostly they either very white in color, or as we age, some people will have brownish, it becomes brown. So it's normally it's the iron oxide that is being added as additives. Yeah.
Yeah. Can you suggest some latest biocompatible metallic implants material other than titanium and steel that can be 3D printed using metallic additive manufacturing? Means we
Well,
just want to know some other.
I think for if you talk about biomedical application, it's either titanium or stainless steel. These are the two gold standard that people use. They don't use any other steel, mainly because of its biocompatibility in nature, and of course its strength purposes, and so on. So I won't be able to recommend. You can try out experiments and so on, but I
Yeah, yeah,
think the gold standard is only these two.
definitely. Okay, so last query we are taking up. Which is better ceramic biomaterial, alumina or zirconia for biomedical purpose?
Of course, there are price difference as well. Alumina is cheaper as compared to zirconia. In terms of property wise, of course, zirconia is much stronger than alumina. And hardness wise, alumina is much harder than zirconia. So again, depends on the application, where is being used. If strength is of concern, then zirconia is the answer. If it is hardness is of concern, then it's alumina. So really, you cannot say which is better. It all depends on application.
Okay. Okay, sir. Thank you so much, sir, for your insightful session. We are highly delighted to have you here for your valuable time and being here for this wonderful session. And also lots of queries have also been responded. And I hope that our participants are really going to be benefited out of it. Thank you so much, sir, for being here with us throughout this session. It was really very interacting one. Thanks a lot, sir.
Thank you, Ravi. Thank you, everybody, and have a nice day. Take
Yeah.
care.
Thank you, sir. Please.
All
Okay,
right.
sir.
Bye.
Yeah. Okay, dear participant, this was session one for today. Another session is just going to be start in couple of minutes. So be here, please, so that we will start another session, and we will discuss about the 4D printing aspects for the biomedical and different other applications. Okay, that's an extensive era of Industry 4.0 and how it is applicable to that. We will discuss about that. So please be here, and we are just going to start the session very soon.
Sir, I request to please share the slide with us, sir, a previous session. Hello, sir.
Yeah, so good afternoon, one and all. So dear participants, for this particular session, we are just initiating this particular session with the perspective of 4D printing. That's an Industry 4.0 perspective. So we will discuss about the various opportunities and challenges. So as you can see over the screen here, so there are various the outlines related to that. So we will discuss about the overview to Industry 4.0 culture, and what about the aspects of additive manufacturing, the various processes for 3D printing, and then we will discuss about the aspects of 4D printing, then smart materials, how the concept of shape memory effect came into picture. So that is just to practicalize this particular aspect of 4D printing here. Then various major aspects and opportunities we will discuss. So here, the very basic fundamental, we are just discussing about the paradigm shift from Industry 1.0 to Industry 4.0, which is the current perspective. In the very beginning, in the late of 17th century. So it was the era where we were talking about the mechanization and the introduction of steam and water power. To next to it, after 1 century here, in the late of 18th century. So it was the time when we were targeting the mass production assembly lines and the discussion about the utilization of the electrical power. And next to that, the Industry 3.0, it was the later phase. So the automation came into picture, the use of computers, IT systems, robotics, etc. And next to that, it is the current scenario where we are dealing with the smart factory, the autonomous systems, Internet of Things, the machine learning, etc. in the current perspective. So these are the different paradigms, how the things are just being shifted from Industry 1.0 to Industry 4.0 up to current perspective. So it is the time where we are dealing about the technology, industry, societal patterns and processes in the 21st century due to increasing interconnectivity and smart automation. So a part of phase here, the industrial change is the joining of technology like artificial intelligence, gene editing, up to the advanced robotics. So we are just dealing all these aspects through ongoing automation of traditional manufacturing, industrial practices, using modern smart technology, the large scale machine to machine communication and Internet of Things. It is very interesting here. This integration is all about improving the overall communication, the self monitoring and the use of smart machine, etc. So as you can see, that Industry 4.0 and the various enablers and the smart technologies for Industry 4.0, the fourth industrial revolution so far. So it is associated with the the autonomous robots, the simulation aspect, the system integration, IoT, IIoT, the big data analytics, the cloud computing, and the very interesting, it is also having the consideration of additive manufacturing. So you can see it is just being highlighted here. So that's an integrated part of Industry 4.0 and we can't ignore it. So to just enable the fully functioning of Industry 4.0, this aspect cannot be ignored. And obviously, on the base of this particular theme of this FDP was planned and up to the applications of biomedical area. It is also called as 3D printing layer to layer of our various experts, Dr. Naren, Piyush, Dr. Sundeep sir, a lot of experts, even Kote sir in previous session means yesterday, they discussed about various aspects of it. So it is freely called as digital manufacturing, rapid prototyping, solid freeform forming, etc. So it is just starting with the forming of a CAD file, STL, and the sliced version. So based on that, then the additively they can be manufactured layer by layer manufacturing, and based on that, if the finishing of the end part is not so far good, so the post processing we can also occupy. Obviously, in our previous class yesterday, Piyush very clearly highlighted the aspect of the support systems, the post-processing, and how and where it is applicable to the 3D printed parts. So there are various methods related with the wet photopolymerization here. Okay, so wet photopolymerization can be associated with that. Then the material jetting, the binder jetting, the material extrusion, the sheet lamination, the powder bed fusion, direct energy deposition, and in the direction of increasing up to this arrow. So you can feel the energy consumption is very high, starting from 1 to 7. So again, these are the one-to-one discussion about the wet photopolymerization, but still, because already a lot of discussion just being made by our previous speakers. So I'm just overviewing these all. So it is the discussion about wet photopolymerization, where the liquid resins are to be deposited over the elevated in the platform, where the product is just being printed out. This is the scene where you can see the aspects of material jetting, where the support materials also being deposited along with the build material. So over the build platform, it is being deposited and the extra material is being cured up by ultraviolet lamps. This is the part, the process, binder jetting this time. So it is very obvious here. We are just binding the metallic materials here, the powder compact form. Okay, once it is being sintered, then with the help of the binder material, it is just being spread over the surface, and the extra binding materials can be cured, as you can see in this particular figure. Here I am highlighting with my this laser pen here. So here we are just curing that additional provided part, so that ultimately the part can be cured and the additional material of the binder can be cured out. This is the most commonly utilized, the material extrusion here, mostly utilized. Almost all the institutions are having these small setups of this methodology. So they can be either of the plunger based, they can be on the filament based, and they either can be on screw based. Okay, it depends what exactly the shape of raw material we are utilizing. If we are utilizing the pellet based, so obviously screw based method must be applicable to that. If it is spools are there, spools means that a real kind of a form where the materials like PLA, ABS, PC, PP we can have. So multiple availability of there in the market. So we can directly just purchase those reels and we can use them as an input. Again, the sheet lamination. So there are two fundamental methods, and also we are utilizing the concept of laser beam cutting here. So they can be procured, and layer by layer fabrication must be just bond, then they can be cut. The powder bed fusion, it is very similar again. Build platform will be there and printed part. So based on that, the laser beam must be targeted over that. So very fine powders are being utilized, and the excess powder form is then removed by the vacuum scheme. The direct energy deposition, so there can be like so the powder form raw material can be utilized in wire form. If the wire is just being faded, so that philosophy is just fundamentally nowadays very commonly known as WAM process, which is a wire assisted additive manufacturing. Okay, so that's a WAM process here. So both are the fundamentally similar. So either we are just in the first figure, you can see the use of the powder based, and second here the wire is faded. Okay, so much the temperature will just provided accordingly, so the deposited material can be applied for the related applications. So if this is a scenario, the different methodologies are being there. So why still there is a need of 4D printing? So versatile applications are being there. So based on that, and also some associated limitations, because some complex geometries, some typical applications are very hard to just get manufactured out of the 3D printing methodology. So we have to go for that. So if we fundamentally talk about 4D printing, it is an extended dimension in terms of time, we can say. So it's an provides provision of additional dimension to the already 3D printed parts into the picture. It was the time when the term coined by Skylar Tibbet. He is a researcher at Massachusetts, the Institute of Technology, MIT. In 2013, he coined the term 4D printing, and he was working in the laboratory at MIT. Self-assembly laboratory is there. He was just coined this term, and particularly the printed part just capable enough to just behave differently under the effect of heat, humidity, light, etc. So these things are being called as external stimuli. If our 3D printed part is capable enough to behave differently under the various conditions of certain external stimuli like heat, humidity, moisture, light, temperature, a lot of stimulus can be used. So if it like the situation, so that can be claimed as 4D printing, because our printed part is just going to behave differently under the atmospheric conditions. So the idea we talk about means that we have to go for some smart materials, also called as active material. They have a versatile capability to respond to external stimuli. So they have to be programmed. It is not like simple that static the sample you have prepared. you have to just go for dynamic printing, definitely. So how that can be done and how it is fundamentally differs, so we will discuss about that in our coming slides. So some of the two different examples I'm just exploring here with some step-by-step images, and these are out of the courtesy of the self-assembly lab of Skylar at MIT. So initially, fundamentally, that the powder crust form of the wooden powder is just being crushed up, and with the help of a smart binder, the spool is just being manufactured, and that particular wood is just being now printed. So once that printed wood is just being here, so it is not a simple printing, it is a 4D printing because we have programmed that. So once that printed part of this wooden material, so it's just being dipped into the smart solution. So after the solution is just soaked up, so once the temperature being keep on changing, so the image, or we can say the behavior of that printed part just keep on changing. So means earlier it was like this, and now how it is, and these images are not random. It is very clear to you that these are well planned, that it was the desire of the manufacturer or the developer. The another example is very similar, like the self-folding cubes. Earlier, they have been printed with smart materials, and then with a phase, like for some specific applications, where all the 6 phases or 6 phase surfaces of that cube are printed separately, okay, attached to each other. But once they have been programmed and they have been allowed to just give one solution, okay, so they are just wings are just coming closer, and that cube is just developed. That's why it is called as a self-folding surface cube. So how this is all happening, this is the principles and the guidelines of 4D printing culture. So the introduction, so based on those applications, that's why I've just discussed those earlier, so that you can at least have some fundamentals in your mind, so that what exactly those applications are doing here. These are the very cases where the human interventions are not possible. Okay, so to avoid that scenario, some robotic attachments can also be made. And fundamentally, the introduction of the 4 dimensions to the 3D printing technology is called as 4D printing. So these are the abilities. So new dimension can have capability to change its shapes by the interventions of the light, heat, electricity, magnetic fields, also humidity as well. By integrating the dimension of time, the printed object have capability to change the shape dynamically, okay, without any electromechanical part or moving part. And if we talk about the versatile applications, they are having a lot of applications where the structures like bending, elongating, twisting, so they are being required in the applications of microtubes, soft robots, toys as well. The process of 4D printing involves using the materials that have the ability to self-assemble and transform when exposed to certain conditions. So here I would like to highlight that the certain conditions means that these are not the random conditions. These are well defined, and according to those conditions, those scenario in which your actually printed part is just going to behave, going to apply their intended functions. So those conditions accordingly we need to plan, and this is called the programmable phase. So we will see how the programming can be made with the help of smart materials. There can be smart polymers. There can be okay. I think there was some connectivity issue. Sorry for that. Okay. Yeah. So just I'm continuing where we have left during that disturbances. Yeah, so we talk about the potential applications. Obviously, there is self-assembly, the furniture, the adaptive infrastructure, the smart tech, etc. Initially, we focus that the examples in our mother nature. The very first image is related with the Venus flytrap. Here you can see here the flyby is just behaving like the stimulus, because by touching the leaves of this particular plant, those wings coming closer and becoming the just maintaining the close position, and ultimately the flyby being captured in between two leaves. So that's a mother nature, and after the time, the things just being over the period of time, the wings are again going to open and they will behave differently. It means that that's the fundamental example of 4D printing culture. What exactly we are talking about here? The another plant is about, we have already, most of us, I think all of us have experience in our childhood related to the same plant. So our finger is just behaving like the stimulus, means that the touch out of our finger to these leaves are just allowing them to become closer, and then over the period of time, then again they let separate it. So how the things are going to be changed over the period of time, over the period of situations, so they makes a difference. So, so it is another example is how the 3D printing and 4D printing are differ. So here you can see that simple material is just being utilized for the 3D printing part. Separate 3D printer we are having. Any methodology we can use being as per the material utilized. And ultimately we are going to have a static structure. But in case of 4D printing, the static structure going to be differ. It will not be static structure anymore. It is ultimately the dynamic intelligent structure. And very specifically, so it can be seen like the multiple smart materials. The material is not conventional one, it is the smart material, and multiple one, not one or two material, multi-material can be utilized for any typical application. And once the static structure out of these smart materials is just being developed or manufactured, the external stimuli means that under the condition of external stimuli, so they can behave differently, and they are not random applications. Some certain applications we have planned with and allow those printed parts to behave smartly under those practical conditions. This is the another the example like here this is any conventional, but how the things are going for in case of 3D to smart materials, definitely you will just and more and enormous problem to find the printing paths, and the static structure is just being formed accordingly, and the stimulus, and we have to program accordingly so that the smart material is just being selected to behave entirely as per the application, and interaction mechanism also being planned accordingly, so that you can sense things are going to behave entirely separate, different in case of the dynamic structure. So again, if to talk about the simple differences between 3D to 4D here, the dynamic shape change possibility was very zero, means that no possibility was there when to think about 3D printing with dynamic shape change for. And for 4D printing, the changes in color, shape, function, everything we can expect. If we talk about materials, obviously in case of 3D printing, the thermoplastics most of time like ABS, PLA, they are being utilized. If we talk about polymer based, if metallic, obviously metals, powder, alloys are being applicable to that. Biomaterials also be utilized, nanomaterials also. But if we talk about 4D printing, so obviously smart materials must be utilized. Smart means like shape memory alloys, shape memory polymers, shape memory gels, hydrogels, obviously self-assembled materials means those have a capability to behave different of memory. So discuss about that in slides. The lithography, SLA processes is being utilized, FDM, SLS, several methodologies are being there, but still in case of multi-material printers, in case of about interesting aspect we discussed. This earlier it was not programmable case of 3D, but fundamentally, the thermomechanical training we can provide to our smart materials and to just behave differently under the different changing scenario. If in case of applications here, you can see even 3D applications in engineering, automotive, aerospace, robotics, etc. Smart textile now is very common. What about 4D printing? Adds dynamic to all the printing applications. It means means dynamically because our product is going to behave under the case of different applications. So you can see because it is a scenario how the things came into picture earlier. So you can see that earlier it was the case because if we directly print our part, it will require a huge printing space, printable area, and obviously it will also cause into the cost of 3D printer because the size is very large. So ultimately to that particular path, we have initially printed it into a different domain with the smart materials. Okay, so it will just require less space. But once the things get changed, the external situation means it can be in case of some moisture content, the humidity, the water involvement, and the power, heat, magnetic field, whatever. So it become the stage 1 become like stage 2, and the printed part become enlarged. Or some typical applications. This is another application where the wings are closer, and over the period of time and temperature conditions, they are just keep on changing. And at the end, you can see this, all the wings are fully open for some typical application, and the space is just open to all. Yes, again, it is a very basic discussion that we are talking about a lot about 4D printing and what about the materials. So if we are just going to have the applications in the domain of where the temperature is just going to change, so they can be concluded as thermo-responsive materials. So for that particular purpose, safe memory materials are being utilized. They can be safe memory alloys, polymers, hydrogels, ceramics as well. If there are variation of water, moisture, so there can be water, moisture, responsive materials can be there. If this is the situation where the variation under the effect of light is just being exposed, so they are being called as the polymer gels being utilized for that particular applications. If variation under the effect of current is just being utilized, if you have wished to just make a product by utilizing the concept of 3D printing, and you will just allow this particular printed part for the application where the current is keep on changing. So obviously the evaporation effect of ethanol and water came into picture, and those materials will be called as electro-responsive materials. If the situations are being like the change in magnetic field, so they will be called as magneto-responsive materials. So it was just about that. So it is then the discussion about that particular field, that the heat. So obviously there is about the shape changing effect. So they are being called as polymers, shape memory polymers, high thermal expansion materials. If the photoresponsive materials are being there, so they can be called as shape memory polymers. And electromagnetic materials are being there, so that they can behave differently. So they are being called as electro-responsive hydrogens. So future smart materials. If we talk about 4D printing, so obviously shape memory materials are being there. So they are fundamentally classified into shape memory alloys, shape memory polymers, hybrid materials, ceramic, and gels as well. So one by one, we will just see that how they can further be classified. It is shape memory polymers, obviously. If they are being they categorized into different forms, obviously the one consideration is must be there. It is the selection of stimulus. So it is not randomized. It is must be planned and well planned and programmed also. So if the material is just being printed out over by the concept of any selected 3D printing method, so under what particular situation this particular the developed product is going to behave, going to apply for a certain function. So whether the temperature is going to behave, change, keep on changing the pH value of this, that any solution, the water, solvent, magnetic material, moisture, humidity, the light, oxidation, reduction. So based on that, we have to think about this kind of shape memory function. So there can be one-way shape memory effect, two-way shape memory effect, triple shape memory effect, or multi-shape memory effect. So in coming slide, we are just coming to that, and then we will come to know that what exactly this shape memory effect is there and how fundamentally they can be utilized. for these 4D printing applications. So the future smart materials again, so the representation about the variety. So fundamentally, they can be like the CUZ and the FEMN, SI silicon based, NIT, PD, copper based, etc. So if we talk about the different shape memory polymers, shape memory alloys, shape memory ceramics having their own versatile application to the different domains. So this is the shape memory polymers, shape memory alloys, and ceramics here. So advantages if we talk about, they are simple to program, biocompatible, biodegradable, and low memory, the self-healing capability. Obviously, if we talk about the disadvantage, as is the case of shape memory polymer. So obviously, the polymer materials are the low of tensile materials strength, the prone to degradation, low thermal conductivity. Obviously, the methodologies can be like the FDM method can be utilized, and the SLA, the SLS material can be utilized. If we talk about the shape memory alloys, so for that particular case, they can be used for the large scale applications, high high tensile strength, because it is much obvious that in this particular case, alloy case, these are the alloy metallic samples. Obviously, they will have a high tensile strength, but obviously at the same time, they will also have to go with high density. And less biocompatible materials are being there because they are the alloy metallic samples. So we have to go with that the composition of that particular, and then accordingly we need to select them wisely. Okay. The concept of shape memory, it means that when the material is just undergone the loading and unloading and heating conditions. So for just example, the stress and strain diagram is just been drawn. So it is just being seen that once it is just provided with the loading condition and unloading, and after the application of heating, so ultimately the material is just behaving like that it was at the initial beginning, means that at the original phase. Another case of shape memory effect means like it is the case of shape memory, and this is about the super elasticity. So once the case of shape elasticity is there, so means that when the loading and unloading condition is there and no involvement of heating and cooling scenario. So for that particular case, it is the case where we can claim it here as super elasticity. This is the very fundamental example, like how the permanent shape, how the programming phase and temporary phase came into picture. So this is the case where we are programming our developed 3D printed material, and this is the temporary phase. Means that once the temperature conditions will be applied, so that ultimately the recovery phase can be seen as a permanent here. Okay. So this is that case where under the different temperature conditions, we have programmed our developed material so that it can, the information can be lodged to that, and the lodged information can be released where the application is ultimately to be provided with. The phase changes, if we talk about some materials, this is the particularly specifically for the case of the shape memory alloys here. The stress, strain, and temperature scenario is just being represented over the period of loading and unloading conditions, heating and cooling conditions. They are just behaving differently under the different structure of material. Okay, so the Mercetine's material is there. The unloading, loading conditions, they are the case. This is the another fundamental diagram, how the things are being planned. Yes, this slide is very interesting. Here, the shape memory hydrogels are being discussed. So whenever we deal with the shape memory hydrogels, two different scenarios are there. Low solution critical temperature and high solution critical temperature. So in both the situations, we need to think that in what particular situation we are going to apply that particular printed part. So once the application is related to the low solution critical temperature, where the solution is being there and temperature keep on increasing, obviously once the temperature just keep on increasing, the overall developed part will behave differently and become shrink material, means the volume ultimately get decreased. If the situation is opposite, then we have to think about the high solution critical temperature situation, where the small material, means the low volume material, it just become large volume material, and vice versa. Okay. So this is a very interesting here. The classes of stimulus responsive materials means that what is to say like a single change, what is to say like one-way shape memory effect, two-way shape memory effect, etc. So this is the case here, the shape memory when the stimulus is applied and shape reverses where the removal of stimulus simply means we are nothing to going with. We are simply making the stimulus on. Suppose this is the case where you have printed a material A that will behave differently, where the heat generation or temperature variation is a stimulus, is going to act as a stimulus. So once you have just pressed your heat exchangers or whatever facility you have appeared with, so you are just changing the conditions, temperature condition, the A product become like B, and once that heat condition or temperature ranging condition become off, then your B material will directly convert to A. So this is nothing simply called single change. So another one is a one-way shape memory, means that after the original shape is recovered from the temporary phase here, a new programming step is required to recreate the temporary phase in each cycle. It means that it is the developed or 3D printed part concluded as A. Once your heating or cooling or moisture, whatever the stimulus is there, it is on, then become like B. And after the application of another stimulus, like suppose in case of here, the water content or moisture content was the stimulus 1, and here the temperature ranging condition. So suppose here when the humidity is just up to the certain level, so A become like B, then B become like A again. So that after the variation of the temperature, so we have to think about that what exactly. So that's why we were talking about that selection of the printable material is to be quite very wisely, should be done very. It is challenging also, but we have to think about a thorough literature and what about the application and how the behavior is going to be changed. And similarly, the two-way or three-way materials are being represented here. If we talk about capability, obviously the self-construction structures, nowadays the people are just organization are developing self-constructed containers, self-curving. If we particularly as per the theme of this particular FDP, it is targeted with medical devices, obviously. So targeted drug delivery, or we can say the release system, it just can be prepared very easily with some smart biocompatible materials, stents, splints, artificial cornea implants as well. The soft robotics can also be the part of applications. So some potential needs, obviously, there can be adaptive structures. Obviously, the 4D printing materials could self-assemble or change their shape as per the environmental features. The programmable materials, another very smart feature of this 4D printing technology. If we talk about the smart medicine, so nowadays it is just being reported in the literature as per the research articles presented by various researchers, investigators around the globe. They have concluded that that can be used for drug delivery systems that can release the medication into the human body for healing up at a faster rate. The 4D printing stands can also be expanded and contract based on the blood flow, so that obviously our medical practitioners are being there, so they can just maintain the blood flow into the human body by providing some external medication. So if the blood flow into any local zone of a human body is just being maintained, so accordingly that 4D printed smart stents can be able to expand or contract them accordingly based on the blood flow. So it is a kind of interactive mechanism, means it is not a kind of a possibility by any certain the 4D printed part, but also it is required with the well collaborated with the medical practitioners as well. Smart textile, very intelligent. It is also called as intelligent textile nowadays. So they can adapt the temperature changes, regulate moisture, and provide better protection in response to the external stimuli. So they will differently behave. If there is a fog, there is a more cold, so obviously they will change their properties because they have been smartly designed. Smart materials, fibers are being included into that. So smart textile is another very good area. Consumer goods again can be produced. These slides are again not because a lot of discussion already been being made about the applications. So manufacturing of smart goods, comfort, car seats, airbags. So once the load is just being applied, so they can become more strengthful. The smart plumbing devices, because so that have a capability so that to maintain the flow, and also so they can just respond to the flux and water demand, so that the diameter of that smart polymeric the plumbing means of plumbing devices, they can vary, so flow rate can be maintained according to the demand. Production possibilities obviously will there, and complex assemblies we will see in next slide that Adidas, the shoe making companies came into picture with the digital light processing methodology, and smartly they have developed the shoe sole with a 4D printing methodology. The smart the textile already been discussed here. Here, this is the case of multi-material gripper having the capability, different four wings are being there, they are programmed accordingly, and under the condition of heating condition, means that once it is came into picture of that keep on changing the temperature condition. Here you can see it is the multi-material gripping, so it is just being developed to grip this particular screw. So at the theme, like earlier at the normal temperature, the wings were open, and as we are keep on changing the temperature situation, suppose for example, it is like 10 degrees, 15, 20 and 60, whatever, it depends that what sort of material we have selected and how it can wear with that increased temperature range. So at the end, the temperature is high here, and now the wings become closer and can pick the material from its base. So because it was the scenario where the normal human intervention cannot be there, it is very tough to maintain that robotic. Also, the space is very complex, very narrow space is there. So no interaction can be made as a human as well as by the robots. These are some certain applications like the that 4D printed smart scaffolds where the space is just being provided, the pores are being there where the cells can be ultimately grown up, and it is very common when the bone fracture conditions is there in case of human beings. So this was the example I was talking about. It is the condition where the carbon digital light, the processing and sintering process is being applied. So this is the Adidas 4D 4D FWD2. So there you can check on Google or over their sites also. So it is just reducing the braking forces and transforming the impact energy into forward motion. So this was the practical application of 4D printing here, and smartly how fundamentally they are being selected. I'm coming directly to the bioorgan printing, how it can be done. So it's an era of the tissue engineering also, where the implantable organs are being rectified and applied. So this is the case where initial phase, the bone defect came into picture. So ultimately we are just injecting the solution to the solution gel transformation to the bone where the defect just came into picture. And this is the case. Second scenario, you can see that the printed scaffolds are being utilized. So if they are 4D printed, means that the architecture, it is fundamentally dominated and well modified here, and that 4D printed smart scaffolds are being applied to the bone defect zone, where we are providing small pores so that ultimately the osteogenesis process can be that more enhanced, and the functional maturation of those cells can come into picture, and ultimately the bone repairment will be arrived as a solution. This is the very fundamental application. We are talking about a lot about the smart drug release system or delivering system. So how the things can be work here, you can see ultimately this is the permanent situation where the wings of that particular the drug or some material, where the drug information is loaded into the implant, and this is the programming phase. So programming under the condition here, so it become like this, the volume is just being minimized, and this is called the temporary phase ultimately. So this is the case where if the temperature of any local area of the human body, suppose in a stomach or some like nearby to knee or liver or heart. So if the local temperature can be increased by providing some certain dose or some medicine by the healthcare practitioner. So if the temperature of that local area is just being increased or raised up to a certain required level, then this particular wings of this medicine, or we can say the printed parts, will become open, because as it is the biocompatible material, and once the wings become open, so the loaded drug will be released into that required local area of the human body. And the physiological environment, obviously I have already told that it will be the physiological condition where the temperature, or maybe it can be related with the blood flow pressure. So obviously it is with the intervention of the medical practitioners, and the drug will be released, and the human being will become healed up. We talk about the smart printable materials. Obviously, considerable parameters can be the safety requirements, obviously the biocompatible materials, and about the tissue specific requirements. This is the technology hype cycle. So what we can expect here, so we are expecting that some of the small era where we can go with the 2 to 5 year target, 5 to 10, and 10 to more than 10 year requirements. So we can highlight here some cases where the 4D printing of smart materials are being picturized. So it will take more than 10 years, because it's an beginning of research and development, and this is an era so that innovation came into picture, and definitely things will become more superior to go with. The 3D printing in industrial manufacturing environment, where The applications like the aerospace, automobile will be arrived over the period of time, and it is expected to go with the 5 to 10 years. This is another situation where obviously the macro 3D printing is still in the development phase, and 3D printed drugs, obviously, I think in our previous session by Piyush and Sandeep sir, someone has asked about the 3D printable drugs also. So they have also been responded very wisely about how this scenario are into the current situation and how the things are going to be changed over the coming period of time. So we have to think about the smart biomaterials, the smart medicines. It is not like that simple as in case of the 3D or 4D printing foods. It is not like that. So we have to think about that, how the compatible materials should be arrived, then only the printing can be proposed. So this is the ongoing research. If we talk about the space exploration, materials are being arrived there, the construction architecture, a lot of applications already being discussed, and obviously in the field of medicine. If we talk about here, the things started in the early of 2000, like 10, 13 here. So 3D printing came into picture as rapid manufacturing, rapid prototyping as well. It was like the material addition process, layer to layer manufacturing. Then the same self-assembly materials came into picture. And in up to it is expected that industrial 4D printing means that it is about the sustainable for towards the industrial as well as some practical mechanical processes and applications as well. So industry application will be explored with the cost of technology, obviously, because without the intervention of or discussion about the economic aspect, the things cannot work. And by 2045, we are expecting to go throughout the sustainable, or we can say the environmental manufacturing here. So for that particular purpose, a lot of software is also available. It is about the Autodesk within the Rhinoceros 3D with grasshoppers. The materialized 4D suits are being there. So they are also very common while we deal with the 3D printing methodology. But additional module of 4D printing also being available with them. The status is the GrabCAD print also. So they are providing the assistance also, including the 4D printing parts. They are also assisting in providing the methodology towards the 4D printing applications. So opportunities, if we talk about, obviously a lot of applications are there. We are dealing with the era of Industry 4.0 and nearly expecting to become like Industry 5.0 with the encourage, obviously, with the use of 4D printing, since it will help in concentrating on the design process rather than manufacturing, obviously, because it is about once the things are being designed very smartly, so we can expect them to get print and the applications can be proposed. Obviously, in the mid of 2025 and up to the end of 25, obviously. So what we can feel that 4D printer with the potential of biomedical sector was proposed by researcher as at Universidad Carlos III de Madrid, UC3M. So they have proposed a smart 4D printer there. So multiple material can be managed. A lot of information are available over the Google. So you can explore. I request you to explore, because as early as more you will just explore it out, so that it will be applicable. And by the end of this year we can we can expect that ICTE was a 4D printed robot that can be assess the quality of the air and soil. So these the biodegradable applications, and obviously were developed by the corporations of Trento University in Italy. So it is expect that correct हुआ था? So there was some uh, interruption issue. That's why so was related to the no that we are in break after this reset. Okay. Yeah, thank you, Gaurav. Conformity. Can anyone can
Yes, is audible.
Yes, sir, you are audible, sir.
audible? Okay, thank you, Prabhakaran sir. Thank you, sir. I think now I must be Gaurav is saying voice is breaking. Gaurav, some issue.
Your voice is clear, but no
I
video.
hope it is now better. Yeah, because it was due to connectivity issue. I have not shared actually. Yes, thank you, Gaurav. Thank you, Dr. Manish, Dr. Prabhakaran sir. Thank you so much. Yes, that's all compile. So I was just sharing about the details of the quiz. No worry about that. Just the compile of this cell have here. Just the compile of that cell have our validatory. Then you will be requested for the test. Link will be shared here as well as YouTube. You will be notified about that, and WhatsApp group here also. Lot of time we will share. Don't worry about that. Okay. So just after that we will do that. And one more thing is that the compilation, because it was a big course, means huge responses we have received. Thank you so much for we have especially to manage 1 or 2 days to so that we can compile the attendance throughout and your testing marks. So both we have to go for build up over the ATAL portal. It is also not great, but so please be patient throughout and just attempt the test, and rest we will do the best from our side. Thank you so much. I'm just resuming my session here, and the remaining slides we will complete very soon. Then it will be done for this session. Thank you so much. For being there, I'm just resuming my discussion. We were discussing about the aspects of the opportunities related to the 4D printing here. And we were there, like we were discussing about the ICTE, which is seen as the 4D printed the robots that can assess the quality of air, and it is further expected to determine the temperature and the humidity of soil and air. So that's going to be very the drastic the application in that particular area. Okay. So obviously the things are being very advanced. So obviously a lot of the challenges and opportunities also being there. So the one it might be my slides are visible or not. Okay, I'm just confirming that.
Visible now, sir.
Slide is visible, sir.
Yeah. Okay. There might be some connectivity lag. Thank you for confirming. So if we are talking about the 4D printed objects, obviously along with the programmable phase, the design softwares need to evolve to facilitate the integration between of the time-based properties and the programming of shape-changing behaviors. Because of the methodologies, the accurate simulation tools need to be predict the shape transformations of the printed parts as well. If we talk about more about the challenges, it is related with the restrictions imposed on the mechanical properties. Obviously, because of this, without the strength, a lot of applications are going to be certainly just get stuck if the certain level of property and strengths are being not there. The scaling up the 4D printed parts, we are the small components of this plant to be printed and programmed and developed for a certain scenario. But what about the bigger applications, means where the scaling up the 4D printed methodology is just being there. So obviously the 4D printed objects are to be consistent enough. The challenge is obviously about the inaccurate actuation, the lack of control of intermediary the stages of deformation, and limited material availability. So as a lot of queries were there in between that, what about the material and well, so obviously the smart materials, smart shape memory materials are being there. So list is so long, but obviously we have to think about the availability as well. We have to obviously explore the list of, or we can see the magazine of materials. It is not all the time possible to find the material from procurement. Sometimes we also have to think about some development of those materials also. Furthermore, the property changes occur as a result of macro scale structural transformations, which may be undesirable, obviously. So some depends, it hardly matters in some applications, but for some typical applications involved. So obviously there can be some different picturization during the process, so that what we can feel that things should not be like that. that we are just keep on changing the shape memory effect and further the stimulus kind of like stimulus A, stimulus B, but the material selection and the application must be targeted so that ultimately this should not happen that under the condition of stimulus A, the properties of that particular materials are being become changed and varied. So again, this is the picturization of the challenges as well. This is one, if talk about the challenges and future opportunities. So a lot of the materials, the software, the commercialization of 4D printing because it's in, still the 3D printing methodology is in the stage of the application and its acceptance at the industry side. So what about the commercialization of 4D printing, the non-bio and degradable final structures? What about that? We have to think about the sustainability and environmental support features of 4D printing. The high resolution 4D printer must be developed throughout. It should not be like the quality of the surface is most of the time. The 3D printing methodologies, if we talk about the FDM and related approaches, triple F methodology is there, approach is there. So obviously because of the staircasing effect, the quality of the surface is not appropriate and we have to always go for some post-processing methodologies. So we have to obviously take care about that. If we will see about the global research institutions, if we are just trying to see, some of you are just very aspirant in the domain of 4D printing, etc. So you must please follow the MIT self-assembly lab reports. They usually over the period of time, the launches and the Harvard's Weiss University Institute of Biologically Inspired Engineering, the University of Wollongong, Australia, the Singapore University of Technology and Design, and many others too. So please keep on searching, keep on just attached and keep on following those research laboratories. They are doing a lot to discuss about that. Yeah, so please, Samik Bhattacharya, please don't try to share. However, it was the last slide of mine, but still, it hardly affect the delivery of this session. But please don't do that because you try to share in between. That's why my slides are gone. However, it was the last slide of mine, but still, it is not appreciable. Please don't do that. Our another session is still left. All the participants are further requested, please don't try to share in between during the session. I don't know what you're trying to share. Please don't do that. Yeah, so it was done from my side. Only the thank you slide was left. So, okay, I'm not going to just sharing it again only for that particular thank you slides. I'm really thankful for you here. I'm saying my and paying my gratitude and thankfulness to your kind presence. Okay. So I have stops here. If any query, we can have some queries if it's still there. Otherwise, we will just compile the session this time and we will meet sharp at 3 as another session that will be the concluding session. The last session we will have for this particular FDP. Then we will just proceed with the schedule. Yeah, any query then please ask. Rest we will compile the session.
Hello, sir. Myself,
Yeah,
Dr.
yeah.
Manish.
Yeah, please ask.
Sir, in which part basically 4D printing material is used
Yeah,
as
lot
in
of
plant
yeah.
materials?
Thank you, Manish,
In
for this
which
nice
body
query.
part, which organs?
Yeah. So a lot of the, yeah, it is being applied in the versatile application of automobile. We have already shared. It depends that what sort of applications we are designed for this particular part. So in the case of biomedical application, it is vastly utilized to develop the stents, splints, as well as the drug releasing systems, where the information about the drug is just being loaded up into the developed part and it is programmed accordingly so that it can be uh, provided or it can be submitted into the human body and into the any local area, and that can be managed according to the principle of 4D printing. So it depends that what sort of application we are targeting. Lot of product we can develop. Thank you.
Okay, thank you, sir. Sir, I also request to please share the slide with us, sir.
Yeah,
It is
definitely.
very informative.
I would love to share my slides. Thank you.
Okay, thank you, sir.
Sir, thank you for your nice presentation. I have one query, sir. Sir, am I audible, sir?
Yes, Vinod. Please. Thank you.
Yes, sir. Sir, actually, as of now, it can be noticed that the 4D printing is mainly focused or utilized for small scale, or you can say that especially in the biomedicals, researcher making hydrogels. Sir, my question is, could you expect means it for heavy industrial applications? Means how the 3D printing, you can say that is adapted in this manufacturing industry as well?
Okay, thank you, Vinod, for your wonderful query in this regard. So definitely, because initially we have to start with the small products, and their functionality must be tested out, evaluated. So once they will just being means observed as per the applications, as per the specifications, then only they can be explored. We can go for the scale up processing, where the small products being developed using this particular concept, they can be explored for some bigger application, means industrial wise. So if the shortcomings are being there at the very beginning, they must be resolved. Then only we should go for some bigger applications. Okay, because at the beginning, if we will try to become like that, so fundamentally, because for the bigger parts, obviously they are being there, but still, these methodologies came into picture only because of the response to the complexity, or we can say the complex applications. So in regard to that, some small complex parts are first to be attempted, and if all things are being going like successfully, then we can go with scale up process.
Thank you, sir, for your explanation. Sir, I have just another query that means I am very interested in this 4D printing. Sir, can you suggest one any institutions, laboratory in our country itself where this work is been going on, or any professors?
Yeah, definitely. Please write a separate mail. Then I will definitely list of some institutions are there. We are also collaborating with them. Okay, at the very beginning, and even at NIT Jalandhar, Dr. Narendra is doing wonderful job there. So they are developing some in small product, but they are dealing with the polymery composite only, called polymery kind of materials. Okay, so yeah, we can suggest more to you. Thank you.
Okay, sir. Thank you, sir. Okay, okay.
Yeah,
Am I
Vijayalakshmi,
audible?
please.
Sir, I would like to, it is very interesting to know that 4D materials are stimuli responsive, and it is supposed to be desirable material, especially for tissue engineering. Can you elaborate more examples how we can use in, means we can succeed in tissue engineering?
Yeah, so most of the time in case of the tissue engineering, we consider the examples of the 4D, even in the case of 3D also, the scaffold manufacturing came into picture. It is related with the bone defects. Mostly we observe in human, if we talk about human body related applications. And some related examples related to the smart toys, smart robotics also. We have explored the examples of smart textiles, where they are the temperature sensing materials are being utilized nowadays, and smart fibers are being associated with that. So once the temperature or changing scenario are related to that, so it is just behave differently. They become like, if the more cold situations are being there, they just try, because of their inherent property, they just try to behave differently. Like they just try to just warm up the human body. So based on that applications, another examples I have shared with you, like the Adidas. So a lot of examples are being there. So they are just part of 4D printing only.
Okay, thank you, sir.
Thank you. Yeah, so dear participant, I think the queries I have also checked the chat box already being done. Thank you so much for this interactive session. I'm really thankful to you all. Okay, so we are just concluding this particular session. This is called as the pre-lunch session here. Okay, so just have a have a rest, have break, have a lunch. So we will meet sharp at 3 p.m. onwards. So we will have another session. Then after that particular session, our concluding session, means like our validity session, will be held. Okay, so that will be done, and after that, your test will be conducted. Thank you so much for being here. Please have a break, and we will see you later. Thank you.